So for our problem, we've set up our axes so that on the two vertical beams we have our y-axis pointing to the left and x pointing up. And for the top beam, normally we've set the y-axis up and the x-axis to the right. We'll have 4 degrees of freedom, theta B, theta C, delta B, and delta C. And the only load acting on our problem is a 6 kips per foot distributed load, which acts along the whole entire left beam, which is 18 feet, which gives us a total force of 108 kips. We know that supports A and D are fixed, so we know that there will be no rotation there. We also know that since there's nothing else acting on it besides this force, the displacements at B and C will be the same, and also the rotations, there will be no rotation since they're fixed joints. They'll stay 90 degrees. We know that the fixed-in moment is negative WL squared over 12, which gives us the negative 162 kips per foot. We know that the moments BA and BC have to be equal, and we know that the moments CB and CD have to equal 0. And we know that using the sum of forces in the x direction, we know that the shear at AB plus the shear at DC is equal to the total force, which is 108 kips. And that's all using the normal sign convention.
Alright, so in order to solve this problem, we're going to use the basic matrix that we've used in class before. So in order to solve the forces in AB, we start at A as the I and use B as the J. So because delta A and theta A are both 0, we can just get rid of those immediately. So for MAB, we just don't even listen to those and just use the 6 over L squared and minus 2 over L. So what we're left with is 6 EI delta B over L squared minus 2 EI theta B over L plus the fixed end moments from AB. We found those earlier. That's negative 162. And when you plug in the length of 18, what you're left with is MAB equals EI delta B over 54 minus EI theta B over 9. And you can solve all the other equations using this matrix the exact same way. Alright, so using that matrix that we just showed you, we were able to get all of the moment equations for each joint. So, as we already said, MAB is EI delta B over 54 minus EI theta B over 9 minus 162 kip feet. MBA is negative EI delta B over 54 plus 2 EI theta B over 9 minus 162 kip feet. And that's with the length of 18 because it's one of the side beams. MBC is negative EI theta B over 6 minus EI theta C over 12. MCB is EI theta B over 12 plus EI theta C over 6, and those are both with the length of 24 because it's the cross beam. MDC is EI delta C over 54 minus EI theta C over 9, and MCB is negative EI delta C over 54 plus 2 EI theta C over 9, and those are both with a length of 18 because that's the other cross beam. Alright, so using the matrix the same way, we can also find the shear forces, and in this case, the way we're solving it, we're going to find the shear forces at A and the shear forces at D. Now at A, you end up with a shear force of negative EI delta B over 486 plus EI theta B over 54 plus the fixed end shear at AB. And that can be easily solved using QL over 2, which in this case is 6 kips per foot times 18 feet over 2, which ends up being 54 kips. And then VDC is exactly the same, except with the opposite degrees of freedom. So it's negative EI delta C over 486 plus EI theta C over 54. Okay, so we need to start solving for these deltas and thetas and everything. And as we said before, one of our equilibrium equations is that MBA equals MBC. And that's because in the positive sign convention, this corner B, you end up with BC going counterclockwise and BA going clockwise. And because of that, one of these has to be negative when you're adding them up and summing these equal to 0 because the moments at B have to equal 0. So because of that, we end up with MBA equals MBC. And using those two equations, MBA equals negative EI delta B over 54 plus 2 EI theta B over 9 minus 162 kip foot, and MBC equals negative EI theta B over 6 minus EI theta C over 12, we end up with an equation of negative EI delta B over 54 plus 7 EI theta B over 18 plus EI theta C over 12 equals 162 kip-foot, and that's our first equilibrium equation. So we use a similar method using at joint C. We have the two moment equations, MCB equals EI theta B over 12 plus EI theta C over 6, and MCD equals negative EI delta C over 54 plus 2 EI theta C over 9. Now at joint C, these two moments in the positive sign convention are going the same direction. So we have to assume that MCB plus MCD equals 0. So when you plug these two equations into this equation, you end up with EI theta B over 12 plus 7 EI theta C over 18 minus EI delta B over 54 equals 0, and that's the second equilibrium equation. So we need one more equilibrium equation to be able to solve this problem. And what we're going to do is use these shears to end up solving it. So we already have the two shears, AB equals negative EI delta C over 486 plus EI theta B over 54 plus 54K, and VDC equals negative EI delta C over 486 plus EI theta C over 54. And what we're doing here is, because this load, the 6 kip per foot load, is only stopped by these two shears, they have to be, this hole has to be in equilibrium. So when you end up taking the sum of the forces in the x direction, you get VAB plus VDC equals 108K. And when you're adding these together, it's important to remember that delta B equals delta C, so you only end up with one delta. So our final equation for this equilibrium equation is EI theta B over 54 plus EI theta C over 54 minus EI delta B over 243 equals 54 kips.
So essentially now with our three equilibrium equations, what we're left with is three equations with three unknowns. So you could solve that a number of ways. You could use a matrix, or what we chose to do is just add joint B, just 7 EI over 18 theta B plus EI over 12 theta C minus EI over 54 delta B equals 162, and from joint C, EI over 12 theta B plus 7 EI over 18 theta C minus EI over 54 delta B equals 0. And so when you subtract so that this term goes to 0, what you get is 11 over 36 EI theta B minus 11 over 36 EI theta C equals 162. So then solving that for theta B, we get 5,832 over 11 EI plus theta C equals theta B. So taking our equilibrium equation from joint C and then plugging in the delta B that we just found, and then solving that, we will get theta B, or delta B equals 26,244 over 11 EI plus 51 theta C over 2 equals delta B. So using our third equilibrium equation of VAB plus VDC equals 108, and then if we plug in the values that we just solved for, then you get EI over 54 parentheses 5832 over 11 EI plus theta C, and in parentheses plus EI over 54 theta C minus EI over 243 times the quantity 26,244 over 11 EI plus 51 theta C over 2, and that all equals 54. So then if you solve for that, you get theta C equals negative 795.27 over EI, theta B equals negative 265 over EI, and delta B equals negative 17,894 over EI. If you take the values for theta B, theta C, and delta B just obtained, and you plug those into the 6 moment equations that we found at the beginning, then you get moment of AB equals negative 464 kip feet, moment BA equals 110 kip foot, moment BC equals 110 kip foot, moment CD equals negative 155 kip foot, moment CD equals positive 155 kip/foot, and moment DC equals negative 243 kip/foot. Even though we have answers for the 6 moments, we're not quite done yet. You want to perform a check. So if you cut it just below joint B and C, and then sum up the shear of BA plus shear CD equals 0. So now that that checks out, we're finally complete with the problem.